Hello calculus fans, and welcome to section 2.2 of the James Stewart calculus textbook, where we are going to continue our talk about the limit of a function. If you remember from last time, in section 2.1 we talked about the tangent and velocity problems, and we talked a little bit about limits, and we used algebra and the graphing calculator to get an idea of how these things work. And we're just going to continue that in this section. So let's look at limits a little more generally and consider numerical and graphical methods for computing them. So let's look at example 1, and it mentions using a table to guess the value of this limit. So what we'll do is we'll use a table in the calculator. So I'm going to go to the y equals screen and punch this in for y1 equals, and then we'll get values very close to 2 but not equal to 2. So go on each side of 2. So we'll approach 2 from numbers less than 2, like 1.5, 1.9, 1.99, 1.999. And also we'll come in from numbers above 2. So like 2.5, 2.1, 2.01, 2.001, and so forth. And we'll see what happens and see if we can guess the value of this limit. With our calculator, we go to y equals, and we want to make sure all these plots that none of them are highlighted. So if one is highlighted, for instance like that, then just go up and hit enter and come on down. And of course make sure these are all cleared out by just pressing clear. And we're going to type in the function we're looking at, which is x squared plus 3x plus 1. We want to investigate this function as x gets really close to 2. So we need to go to the table, which is above the graph. We go to second table. And with this setting that this table is on, it scrolls through, but it won't let me choose a number by plugging it in, and it won't let me delete anything. So if I hit delete, nothing happens. So if your table is set up like this, we need to make a change. So if you look above the window key, it says table set. So you want to go second table set, and you just want to make sure the independent variable is on ask. So you want it to look like this. The table startup and the change in the table doesn't matter. We just need ask and auto. If it's set like that, then when I go to second table, I can just plug in values. So I could plug in values a little bit below 2, like for instance 1.5, 1.9, and it's evaluating the function at these points, 1.99. Now with this one, it's a simple polynomial, so we could actually just plug in 2. And you can plug in 2 right here, and you see that the function is 11 evaluated at 2. But typically what will happen is we won't be able to plug in a 2. When the functions are more complicated, we need to plug in a 2, you would typically get a division by 0. So we're just sort of playing a little bit here to see what would happen if we couldn't plug in 2. So let's say I can't plug in 2. So I'm going to come in from numbers now above 2, like 2.5, 2.1, 2.01, and you can see it looks like we're approaching 11 as we approach 2. It looks like the function is getting closer and closer to 11 as we come in values below 2 and also values from above 2. So here you see a picture of the graph of this function, and you can see from the graph it does appear that as we approach 2, this function gets closer and closer to 11, which we know it does because we know that we could actually plug in 2, and that function evaluated at 2 is actually 11. So let's look at an informal definition of a limit. So suppose we have this function f of x defined on both sides of a, except possibly at a itself. That's an important point. We're going to see that we don't really care what happens at the point a. We only care what happens as we get really close to a on both sides of a. And then we write this, and the way this is read is the limit as x approaches a of f of x equals L. One thing we have to keep in mind is this L this L has to be a number. So that'll become important later, but L has to be a number. And we say that if we can make the values of f of x, this function, if we can make the values of this function arbitrarily close to L. And by arbitrarily close, we mean as close as we want. That's what it means. You'll see this language arbitrarily close when you're dealing with limits. Just remember, it means as close as we want. We can make the values of this function, f of x, get as close as we want to L, the limit L, by taking values of x sufficiently close to a on either side of a. So on either side of a, so in our case, a was 2. So we can take values of x sufficiently close to a on either side of a, but again, a key is not equal to a. We don't care what happens at a. Only what happens is we get really close to a on each side of a. All right, calculus fans, here is a question for you. Keep in mind what we just talked about. We want to know in which of these cases below is this condition satisfied? Is the limit as x approaches a of f of x equal to L satisfied? We've got 3 cases here. Similar, but little differences. So this is just a function f of x. I guess maybe I should have mentioned that this is y equals f of x in each case. And in the first case, you just got this continuous function here. Second case, you got a hole in the graph here at a. In the third case, you got a hole in the graph at a, but the function of f of a is defined at this y value here, not equal to L. So if you want to know in which of the cases below is this condition satisfied, you can pause the video if you want to take a, think about it and see what you think. But we can see that in this case, it's definitely, the condition is satisfied because we can make this function be as close as we want to L just by getting our x values close enough to a. In fact, in this case, we could just plug in a and we would get exactly L. Now in this case, you can see as x approaches a from the left or the right, we can't actually get to a because the function is not defined at a. But the key is, you can see it right above here, we don't care what happens at a. So if you think about what's really happening, there's this one hole in this graph at L. But isn't it true we could get this function is infinitely close to L from numbers just above L and also numbers just below L just by getting our x values close enough to a, either below a or above a? I mean, if this number is 7, let's say L is 7 in this case, couldn't I find an x value that could make this function be 6.99999? And if that's not close enough, how about 6.9999999? I mean, I could keep going, right? You can make this function be as close to L as we want just by getting x close enough to a, but not equal to a. So this also satisfies this condition, even though we can see by looking that f of a does not exist. The key being we don't care what happens at a, only what happens close to a. Now in this last case, we can see that f of a is not equal to L. Right? There's a hole in the graph here at a, but the function is redefined so that f of a equals this number here, whatever this y coordinate is. But again, we don't care what happens at a. We could still make this function be as close to L as we want just by getting x to be close enough to a, either less than a or greater than a, so that in all 3 of these cases, this condition is satisfied. And the whole key is that we don't care what happens at a when it comes to the limit. So that's the note here. We need to make sure that we understand that regarding the limit, regarding the limit, we don't care what happens to the function at a. And that's going to be really important later on. The function at a. It's an important point. We don't care what happens at a. The function doesn't even have to exist at a, or the function could exist but not be equal to the limit L. So just to be clear, what we've shown here is this limit exists in all three cases. This is satisfied. So in all three cases, the limit as x approaches a of f of x equals L. The limit exists in all three cases. So now let's consider some of these limits where you actually cannot plug in a 1. If you plug in a 1 here, you can see we're going to get a division by 0 down here. We're also going to get a 0 up here. So if I actually just plug in a 1, I'm going to get 1 minus 1, which is 0, and 1 squared minus 1, which is also 0. So I have 0 over 0. So unlike the previous polynomial case, we can't actually plug in 1. So we really do have to do some sort of educated guess here. So why don't you take a minute here, plug this into your graphing calculator, and plug in values really close to 1 but not equal to 1. Values a little bit bigger than 1, a little bit smaller than 1, and see if you can guess the limit. Now remember, in your calculator to plug this in, if we go y1 equals, you have to be careful to make sure you get order of operations right. So you may have to do something like this, but you're going to want to use parentheses. If I leave these parentheses off, I'm going to get the wrong thing, right? This is like just some algebra here. If I go x minus 1 divided by x squared minus 1, order of operations is going to look at this division and do this first. And we're going to get something that we don't want. So just be careful. Make sure that you use parentheses, unless if you have some of the versions of the software have math print, what TI calls math print, so then it will actually look like this, then you don't really have to worry about it. But if you have an older version that doesn't have math print, then you're going to need to use parentheses here. When I work on this problem, here is what I got with my graphing calculator. This one has the older style, so it doesn't have the math print, so I needed to use the parentheses to make sure it worked out right. And here's the results of the table, and it looks like we could make this function be as close to 1/2 as we want to, just by making x be close enough to 1. So that we could say that the limit as x approaches 1 of x minus 1 over x squared minus 1 equals 1/2. Now we are just guessing. This is no proof. This is we're making educated guesses just by plugging this into the calculator, getting this really close to 1, and just guessing. It looks like we could make this as close to 1/2 as we want to by making x be close enough to 1. Now it turns out this is actually true, but just to keep in mind at this point we're just making educated guesses. But while we're here, I'm going to ask you a question and see what you think. You can see that if I plug in a 1 here, and we're going to get 0 over 0. So what if I said to you 0 over 0 is equal to 2/17? Would you believe me? And what if, to back up my claim, I said, well, if you don't believe me, just take the cross products and you can see it's true, because 0 times 17 equals 0 times 2. That's my proof. Good enough? Hopefully you're a little skeptical about that proof because it's a little shady. It's definitely a little bit shady. So what I'm doing is, you probably remember in algebra, you talked about proportions, and you said something like if A over B equals C over D, then the cross products would be equal. This times this equals this times this, which is true. A times D equals B times C. And a lot of times you'll use this And you can think of plenty of examples. 2/5 is equal to 4/10. And if you take the cross products, they're equal. 2 times 10 is 20. 5 times 4 is 20. But although this is true, my argument is not true because I failed the first part. If A times B is the same as C times D, then we can say this. So this first if part is failed because this is not true. So that whole argument seemed a little shady, and in fact it was a little shady. But here we have a nice looking problem, and I know some of you guys have been waiting to see a trig function, so here you go. The limit as x approaches 0 sine of x over x. Well, as we plug in a 0 to the sine function, this is one of them we have to know. So let's do a quick review, because we absolutely, as a Calculus 1 student, we have to know 2 trig functions without any hesitation. We need to know at least a period of the sine function and a period of the cosine function. So for a quick review here, I'm going to draw the sine graph and the cosine graph. The independent variable is the angle in radians. And if you remember, sine and cosine are both locked between -1 and 1, so the range is -1 to 1. And sine, the sine of 0 is 0. Sine goes through the origin, right? So when I graph the sine function, it goes something like this. So the sine of 0 is 0. Sine of pi over 2 is 1. And then all the integer multiples of pi are going to be 0. Because remember, of course, it goes on forever in this direction and also in this direction. And cosine is just this graph shifted over, right? It's shifted over pi halves. So the cosine of 0 is 1. The cosine graph looks like this, goes through here, back up here, so that the cosine of 0 is 1, cosine of pi over 2 is 0. And these graphs are going to come up so frequently in calculus that we have to know these. So if you're rusty on these, you need to make sure you can just sketch these. Just every once in a while, just make sure you can sketch them. This is a pretty ugly looking graph, actually, now that I look at it, the way I sketched it here. But these 2 graphs are important. If we know these 2, then we can get a lot of other information. Because remember, out of the 6 trig functions, which are just ratios, if you know sine and cosine, you can get all the rest of them, because they can all be written in terms of sines and cosines. So with that in mind, let's consider this limit. The limit as x approaches 0 is sine of x over x. And you can see that sine, if I just plug in the 0, sine of 0 is 0. And then I get another 0 here. So we're getting what's called an indeterminate form of 0 over 0, which we will spend a lot of time on very soon. And basically, when you have this indeterminate form, when there's a limit approaching 0 divided by another limit approaching 0, which is basically what we've got here, this indeterminate form can actually be anything at all. So it all depends on which function is getting to 0 quicker, the numerator or the denominator. But we'll talk a lot about that later. But right now, all we can really do at this point, we just have a graphing calculator and some algebra. We don't really have any calculus to use yet. So what we'll have to do is punch this into the calculator. Now it's important to make sure you're in radian mode, not degree mode. Now the TI-83 and 84 will come default in radian mode. But just to check, if you press the mode button, you just want to make sure you're in radian mode when you do this. And if you play around with it a little bit, you'll see that it looks like, again, we're making an educated guess, but it looks like the limit of this is 1. And when you graph this at 0, of course it's not defined at 0, but the curve goes something like this. It kind of comes up like this, and the y-coordinate right here is 1, actually. So if you play around with the calculator like we've been doing, plunge this in for y1 and use your table and get really close to 0 using values like -0.1, -0.01, -0.001. and then also values just a little bit above 0, like maybe 0.1, 0.01, 0.001. You see that you can make this function get seemingly as close to 1 as you want by just letting x get closer and closer to 0. And again, we're making an educated guess. Turns out that we're right, but we don't always want to guess. And there are some pitfalls of guessing. So to see some pitfalls of guessing, in this Stewart textbook, there are example 2, example 4, and example 5 in the book. But basically just shows that sometimes guessing can be misleading, and it's not a huge problem for us because we're only guessing right now because that's all we can do. But we're going to learn some techniques where guessing won't be too much of an issue. So, but if you do want to see some where guessing can lead you astray, there's a few examples in the book. And also, you don't always want to rely on your calculator too much. So just an example. I know the TI 83 and 84 are really nice calculators. I've used them for years. They're really user-friendly, and I really like them. But they're not perfect. So, if you don't believe me, ask your calculator this question. 10 to the 15th power plus, I don't know, let's say 917 minus 10 to the 15th power. Now, this should be pretty easy, right? The answer is clearly 917. But there's a little bit of a problem with the calculator. With TI 83 and 84, they don't have computer algebra software. They use what's called the Cordic algorithm. And the Cordic algorithm is more of it goes through an iterative process, and there's no what you would call thinking, I guess. There's no computer algebra software, so this is going to cause problems in the memory. And then when you try to add this, it's not going to be able to handle that very well. So it actually won't add this. Then when you subtract that, your calculator is going to tell you 0 right here, which is clearly not 0. So your calculator is great, does great things, but don't believe everything it says. All calculators and calculating devices and computers, they all have little quirks. And so we don't want to rely on them completely. We still want to have some intuition so that we know when something has gone wrong or something doesn't seem right. We also have to be proficient with what's called one-sided limits. Notice the notation here. What this says is x approaches a from the left. The little superscript negative on the right. Notice this is on the right of the a. If you put it on the left of a, it could be confused for a negative a. So it's got to be on the right side as a superscript. This is the limit as x approaches a from the left of f of x equals L. And this is called the left-hand limit. Now that name makes sense because really what's happening is this. So here's our number line here is A. And if we're approaching A from the left, so we're coming in from this direction, this is the limit as x approaches A from the left. So we're looking at the function itself as x approaches this number A from the left. And this is called the left-hand limit. Now this other notation here, the limit as x approaches A from the right. So you have a superscript plus sign. That's just the opposite case. So that's where we're coming in, or approaching A from numbers of bigger than A. From the right, on the number line, numbers from the right are bigger. So we're coming in from the right. So this would be when we're considering the limit as x approaches A from the right. So notice its notation is going to be more and more important the higher you go in math. So notice that this A is to the right of A. It's not negative A. I can't say this. If I say the limit as x approaches negative A, that's a completely different thing. We don't want that. So it's a limit as x approaches A from the left, and the limit as x approaches A from the right, which in this case, of course, would be called the right-hand limit. And again, the name left-hand and right-hand limit comes from the fact that on the number line, numbers to the right are bigger, right? So on the number line, you've got a 0 here, 1, 2, 3, -1, -2, -3. So as you come in from the right, these are bigger numbers. If I approach 0 from the right, I'm approaching 0 from numbers bigger than 0. If I approach 0 from the left, I'm approaching 0 from numbers less than 0, as all these negatives are less than 0. So that's where the name comes from. And then this is going to be very familiar. This notation here, the way we write this, the limit as x approaches a from the left of f of x equals L. We write this and we say the limit of f of x as x approaches a from the left, so in this case from the left, is equal to L if we can make the values of f of x arbitrarily close to L, which means, again, as close as we want, by taking values of x sufficiently close to a and x less than a. Remember, we don't care what happens at a. It's not less than or equal to a. It's less than a. We're never going to get to a. We're going to approach a from the left, but we're never going to get there. We're going to get infinitely close to a, but we're not going to get to a. And similarly, over here we write this notation and we say the limit of f of x as x approaches a from the right is equal to L if we can make the values of f of x arbitrarily close to L, which means, again, as close as we want, by taking the values of x sufficiently close to a and x greater than a. So it's very similar. The one-sided limits are a lot like the limit without the one side. So the typical limit where we don't have this notation, which we'll see later, means that it actually includes both of these. But the one-sided limit is very similar to how we were talking about limits originally. We're just approaching from just one side. And we're still going to think of it as I can make this function, whatever this function is, I can get it as close to L as I want to. I can make it within a billionth of L, within a trillionth of L, as close as I want, just by getting x close enough to a, and in this case, less than a. So I mentioned this, that there was a relationship between one-sided and two-sided limits. And the two-sided limits are just the typical limits. So when we first started talking about limits, they didn't really mention it, but they're actually two-sided. So what this says is the limit as x approaches a of f of x equals L if and only if. This IFF just means if and only if. It's a biconditional statement. So sometimes you'll see the symbol for a biconditional statement that looks like this, like a two-headed arrow. It's just an if statement that reads in both directions. So that this is true if and only if this is true. So basically what it says is that this left-hand limit equals L and the right-hand limit equals L. They both have to equal L for the two-sided limit, or what we typically just call the limit, to equal L. So it's sort of like as you approach this x, the function itself has to approach L from both sides, from the left and the right, in order for this to be true. And this biconditional statement, it's just like, it's an if statement that reads in both directions. So typically in English, we have a conditional if statement, like, if it rains, then I'll take an umbrella. But I can't reverse that and say, if I take an umbrella, then it will rain, right? Because it's just a conditional if. Biconditional if just means if this, then this, and also if this, then this. So let's take a look at what this actually means. If we look at this example here, we've got this function, and we're saying that the limit is x approaches 2, so x, now x is approaching 2, right? Here's the x-axis, x is approaching 2, either from the left or from the right. And then the function, which is the red curve, right? This function is approaching 1. So as x gets really close to 2, so if I follow this along, x is coming in here. As x does that, this function is going along here. So it appears that as x approaches 2 from the left, this function is approaching 1, right? It's approaching 1. Also, as x approaches 2 from the right, so x is coming along the x-axis here, approaching 2, and as x approaches 2, the function is also approaching 1. So that this holds as x approaches 1 from the left, I get 1. As x approaches 2 from the left, the function is approaching 1. Also, as x approaches 2 from the right, the function equals 1, so that we could say this is true. So the as x approaches 2 from the left and the right, they both have to equal the same L. And if that happens, then the limit as x approaches that number of f of x will also be equal to L. So here's an example of that. So here's another problem for some practice. You've got this function with this discontinuity at 1. It's got what's called a jump discontinuity, jumps up here. So see if you can figure these out. We've got the first one is the limit as x approaches 1 from the left of this function. So a one-sided limit as we're coming in here. What is this function approaching? And then likewise, we've got the one-sided limit from the right. And we've got the two-sided limit, or what we typically just call the limit. And then we've also got something from an algebra class, just asking for the value of the function at 1. So what you should do is just pause the video and see what you can come up with here. And when you have an answer, go ahead and turn the video back on. Okay, so hopefully you actually paused and thought about this for a second. If not, take a second and do this. This is how you learn. You have to go through these little speed bumps along your process of learning. Otherwise, you won't learn as effectively. So, okay. Hopefully you came up with what you think is the answer, and let's take a look at this. So this one is the limit as x approaches 1 from the left of f of x. So x is approaching 1. So here's the x-axis, right? So as x travels along here approaching 1, the function f of x, which is the red curve, as x approaches 1 from the left, the function looks like it's approaching 1. Now remember, we don't care what happens at 1. But this picture is supposed to show that you can make this curve be as close to 1 as you want just by getting x close enough to 1 from the left of 1. So the answer to this one, this answer is 1. Because we can make this red curve as close to 1 as we want, right? Because there's a hole in the graph, which means that although we can't get to 1, we can get to 0.9999, right? Or even closer to 1. We can get as close as we want just by getting this as close as we want to 1. Now, as we approach 1 from the right, so as x is coming in along here, I'm on the x-axis, x is coming along here. Well, as x does this, f of x is doing this, right? So as x goes along here, imagine these two things being linked together. So as I slide x along here, the y value slides along here. So I can get x's. As x gets closer and closer to 1 from the right, this gets closer and closer and closer to 2. Now my picture's not perfect here. Maybe this 2 should have been right here. Maybe that'd be a little bit better. So what I was trying to show is that as x approaches 1 from the right, this thing is approaching 2. It's kind of a bad picture, but it's supposed to be approaching 2. Right, so x is approaching 1 from the right, and this curve is sliding along here, getting closer and closer to 2. So then when we ask this question, what about the limit of this function at 1? Well, as I approach 1 from each side, these two have to be connecting. They have to be both coming into the same point, right? They have to have the same, these have to have the same limiting value, which here they don't. So when this happens, what we say is that this function does not exist. The reason it doesn't exist, we can do something like this. Left-hand limit is not equal to the right-hand limit. That's all we have to show. Something like this. L's there. Left-hand limit does not equal the right-hand limit. And because of that, the limit does not exist, right? It fails this. These numbers have to be the same. So what about this? F of 1, the function evaluated at 1. So when I plug in a 1, it's not defined there. It's actually equal to 2. That is equal to 2. So hopefully that makes sense. If not, we're going to do quite a few more examples. So hopefully they'll make sense after you see the rest of these. All right, so here is one to try out. Example 4 is referring to problem number 4 on page 92. And we've got the problem listed here. Got a picture down here of our function. And we've got some questions here, A through F. So what you should do right now is try these out, see what you come up with, and then, of course, pause the video, see what you come up with, and then come on back. Okay, so hopefully you tried these out, and let's take a look. So we've got this function here. We want to know the limit as x approaches 2 from the left of f of x. So remember, x is now approaching 2 from the left. So think of this x-axis. We're approaching 2. As we're coming in approaching 2, we're on this branch up here, right? As we're approaching 2 from the left, we're on this branch. But if we're approaching 2 from the right, then we'd be on this branch. So for problem number A, x is approaching 2 from the left, and this function f of x appears to be approaching 3. So the answer to part A would be 3. For part B, now x is approaching 2 from the right. So as x approaches 2 from the right, we are on this branch. So as x approaches 2, this function is approaching 1. So the answer to this is going to be 1. Part C is just x approaches 2, so it's like a two-sided limit. So as x approaches 2, what is the function doing? Well, that limit doesn't exist because these two numbers we just came up with are not the same. So if these two numbers, the limit as x approaches 2 from the left of this function, is not equal to the limit as x approaches 2 from the right of that function, that means that the limit as x approaches 2 of that function does not exist. So for part C, the answer is does not exist. Part D, this is just what is the value of the function at 2. So when x is 2, what's the value of the function? So when x is 2, the value of the function is 3, because it's undefined here, so f of 2 is actually equal to 3. So let's see, for part E, the limit as x approaches 4 of f of x. So this one's a little easier to work with. So we're talking about 4 as x approaches 4. Now in this case, the left hand and the right hand limit are both approaching the same number. But what about this hole? There's a hole right at 4. Is that a problem? Well, remember, do we care what happens at 4? We actually don't. We don't care if that function's not defined at 4, which it's not. There's a hole in the graph at 4, but we don't care. We can still see that we could make this function get as close to this value as we want just by getting close enough to 4. And again, we don't care what happens at 4, so we don't care that the function's not defined at 4. We don't care. There's a hole there, doesn't matter. We can still make this function get as close to 4 as we want just by getting x close enough to 4 on either side of 4. So the answer to part E is just 4. And this we just talked about a second ago when we were talking about this part, but the function at 4, well, there's a hole there, so it just is not defined. So f of 4 does not exist, or you could say it's undefined. However you want to say that. Does not exist or is undefined. Either one is okay. So let's take a look at another example. Example 5 on the handout refers to problem number 6 on page 92. Okay, so I've got the picture right here. If you have your book, you know, of course you can use your book, but this is the picture of this problem. So you know what to do. Don't wait for me. You have to try these out. If you don't go through the process of learning how to do this on your own, you're not going to learn it. So do the right thing. Pause the video, try to figure these out, and then when you have your answers, come on back. But I will give you a heads up on one of these. Right around here, there's something that the book is trying to show, and it's really difficult to show with a static picture. So they're trying to show that as you approach here, it just oscillates more and more. So keep that in mind, and I'll give you an example on the calculator afterward that makes it a little easier to see what they're trying to show. All right, so let's take a look at these and see what we come up with. So for part A, we've got the limit as x approaches -3 from the left of this function h of x. So we're approaching -3 from the left, from values below -3. So as x comes in along here, I'm up on this branch, and this is approaching what looks like, let's see, 1, 2, 3, 4. It's approaching 4. Again, we don't care what happens at -3. We just care what happens as we approach -3. And as x approaches -3 from the left, this function is getting closer and closer to 4. B, as x approaches -3 from the right, so now we're approaching -3 from the right, so we're coming in along here, and now we are going up here, and it also is approaching 4. So then part C says, what's the limit of this function as x approaches -3? Well, we've just seen that as x approaches -3 from the left and the right, we get 4 in both cases. So the answer to this one for the two-sided limit is 4. So part D says, what is h of -3? H of -3, well, there's a hole in the graph, which means that function is not defined there. So we can say for part D, h of -3 does not exist, or is undefined, however you want to say it. Okay, part E, the limit as x approaches 0 from the left. So x is approaching 0 from the left. So as x approaches 0, we're on this branch of the curve of the function h of x. So as x approaches 0 from the left, this thing is approaching 1. All right, so the next one, F, says the limit as x approaches 0 from the right of h of x. So x is approaching 0 from the right, and as x approaches 0 from the right, the function is approaching -1. So this one would be a -1 for F. And then G says the limit as x approaches 0. Well, for this one, we can see by the answers to E and F, the fact that they are different means that this limit doesn't exist. So as you approach 0, the answer depends on which side of 0 you approach from. If you approach 0 from the left, the function is approaching 1. As x approaches 0 from the right, the function is approaching -1. So since those two are different, then the limit as x approaches 0 just does not exist, because the left-hand limit does not equal the right-hand limit, so that limit doesn't exist. So H says, what is the value of the function at 0, right? H of 0. So H of 0, we look at this, we've got an open here, which means that the function is not defined there, but the closed dot here means that H of 0 is 1. So H is 1, the answer to H. And then we've got I is the limit as x approaches 2. So you look at the 2 here. Just looking at what the graph is doing, the graph of the function as x approaches 2, from the left or from the right, they're heading to the same spot. They're heading to this y value of 2. The fact that the function doesn't exist at 2 doesn't matter, because remember, we don't care what happens at 2. The limit of h of x is x approaches 2. We don't care what happens at 2. But you can see that as we get really close to 2, we can make this function be as close to a y value of 2 as we want to. So that the answer to that for part I is 2. And let's see, part J continues down here. So h of 2. Well, h of 2, there's a hole in the graph at 2, so the function is not defined there. So we could say h of 2 does not exist. And then for J, the limit of h of x is x approaches 5 from the right. Okay, so here's 5. Here's where it gets a little weird in here. So as h approaches 5 from the right, what this picture shows is that there's really nothing crazy happening as we approach 5 from the right. All the craziness happens as we approach it from the left. But from the right, this is just going down to whatever that y value is right there, which is a 3. So as x approaches 5 from the right, the function is approaching 3. Okay, so that one's not too bad, but on this next part is the limit is of h of x is x approaches 5 from the left. So now x is approaching 5, so x is coming in here, approaching 5, and as that happens, you can see this seems to oscillate faster and faster and faster. And it's hard to show this on a static graph, so this one's a little tricky to really understand completely unless somebody explains what they're trying to show here. Where they're trying to show that as you get closer and closer to 5 from the left, this oscillates more and more and more, so that the limit does not exist because the limit never approaches any one number. So for the limit to exist, there has to be a number that the function gets closer and closer and closer to. But in this case, it doesn't. It oscillates indefinitely and never approaches any one number. So I'm going to show you an example of this on the graphing calculator because it's a little easier to see than it is with just a static picture like this. The graph that I want to show you is the graph of sine of 1 over x. So I went to y equals in the graphing calculator and just typed in sine of 1 over x. And then to graph it, I'm going to go to zoom and do zoom 7, zoom trig. So it will just graph, like if you're going to make a regular graph of a sine function or something like that. And you can see around the origin, it does something a little strange. So let's try to zoom in around the origin, because around 0 is where this is going to get really weird. So if I zoom in, I'm going to zoom in right at the origin, and just watch what happens as you zoom in. But a lot of times when you zoom in, things become more clear. But in a graph like this, when you zoom in, they become more unclear. So I'll zoom in one more time, right at the origin again. And you can see that it just doesn't seem to settle. It just gets more and more chaotic around the origin. So that graph, as you approach 0, it just doesn't exist. The limit as x approaches 0 of sine of 1 over x does not exist. And that's what they're trying to show in the book, that as you zoom in, it just gets worse and worse. So just to make sure we're all clear here, so what we just did on the graphing calculator was you looked at this question, the limit as x approaches 0 of sine of 1 over x. And this limit does not exist because the limit never approaches any one number. And that's sort of like what I think they're trying to show here. And now we're ready to talk about infinite limits. So sometimes limits fail to exist because the values of the function increase or decrease without bound. So suppose f of x is defined on both sides of a, except possibly at a itself. Again, we don't care what happens at a. Then the limit as x approaches a of the function equals infinity or negative infinity means that the values of this function can be made arbitrarily large. So there's that language again. Arbitrarily large just means as large as we want, or large negative, right? Or large negative in the case of a negative infinity. by taking values of x sufficiently close to a but not equal to a. And again, we're talking about not equal to a. We don't care what happens at a. All right, so let's look at this example of a limit like this. We've got the limit as x approaches 0 of 1 over x to the fourth. We can analytically think about what's going to happen here. If we put in like real tiny numbers in here and raise them to the fourth power, because x is approaching 0, so if you put a really small number and raise it to the fourth power, it actually becomes even more small, right? Like even numbers between -1 and 1, when you raise them to powers, they get smaller to even powers. So if I take like 1/2 and raise it to the fourth power, it becomes 1/16. Well, 1 divided by 1/16, the small number down here in the denominator is going to make the entire fraction bigger. So the closer this denominator gets to 0, the bigger the fraction overall gets. And you can see that reflected in the graph here. So as I approach 0 from the left or the right, this thing gets really big, really fast. Or you could see it here. If you plug in 1 over x to the fourth as in your calculator and go to the table and just punch in a few values here, you see if I let x be 1, 1 over 1 to the fourth is 1. But then when it's 1/2, you get 16. When it's 0.1, you get 10,000. And you can see these things are getting big really quickly. This, your calculator would say 1e8, which is kind of an old notation from the old days with an electric calculator. If you remember ever seeing anything like this, your electronic calculators in the late 70s could make things as long as they could form it out of a character like this. So there was no way to write scientific notation back then. So what they did is they put this e that meant exponent. And so this is really saying 1 times 10 to the 8th power. So 1 with 8 zeros. So it gets big fast. So that you could basically, the way we can think of this is we can make this number, 1 over x to the fourth, as big as we want to just by making x small enough, making it close enough to 0 on either side of 0, right? Because you're going to raise it to the fourth power anyway, so negative numbers wouldn't matter. So that we can say that the limit of this is equal to infinity. But if you remember before when we talked about limits, we said the limit has to equal L, and L had to be a real number. So when we say this equals infinity, what we are really saying is that f of x increases without bound as x approaches 0. So that means f of x, which in this case is this function, we can make this function as large as we want by just making x as close to 0 as we need. So with this notation, that's what it means. So technically this limit does not exist because this is not a real number. I'm going to add a little note here, and this note is important for us when it comes to limits. So here's what we're saying. So infinity is not a number, of course, and L, the limit, must be a number. So what we're saying is this limit does not exist. There are a number of ways that limits cannot exist. In our case, the particular way in which this limit doesn't exist is that it is unbounded. It increases without bound. So this statement is true. This statement is also true. So when you have a limit that's equal to infinity, then by definition almost, it doesn't exist because infinity is not a number L. So these both say they don't exist, but this one is better. This gives us more information. This tells us why the limit doesn't exist. This says not only does the limit not exist, it doesn't exist because it grows without bound. The limit is infinity. This is a particular way in which the limit doesn't exist. And there's a little note in the textbook. They have a little symbol that looks like this, looks like a 0 with a slash through it. And this is on page 89. And they talk about this. So if you have a question like this in a calculus class, so let's say this is the question, the answer we're looking for is this. While this is true, this is better. This would be like if you're in some math class, maybe I don't know, middle school math. Let's say you're tutoring. Let's say you are tutoring a beginning math student, and they have a question, and the question is, what's the square root of 25? Let's say the student says, oh, I know the answer to this one. I know this one. The answer is it's a positive number. Maybe they're talking about the principal square root or the positive square root, and you're like, well, that's true. That is true. The answer to this is going to be a positive number, but there's a better answer. A better answer is to say the square root of 25 equals 5, right? So, yeah, this is true, but this is better. And that's a little bit like this. These are both true statements. This one's better. So as a Calculus 1 student, if you see this as a question, this is the answer you want. If you want to get complete credit, all credit, you want this answer, not this one. So again, if you want more clarity on that, the book will basically say the same thing here on page 89. All right, one more example along these lines. The limit as x approaches 0 of 1 over x. Everyone has probably seen this graph before. And it goes something like this. Something along these lines. My drawings are never the greatest, obviously, but it looks something like this. So if you're going to answer this question, the limit as x approaches 0. So approaching 0 from the left and from the right. You can see right away there are going to be problems with this question, or with the answer actually, because if we consider the limit as x approaches 0 from the right of 1 over x, so we're approaching 0 from the right, we're coming in along here. As we do that, the function 1 over x is going to infinity. So from the right, it's going towards infinity, but if we approach 0 from the left of the same function, so now we're coming over here, approaching 0 from the left, and the function itself is now approaching negative infinity. So this limit, the two-sided limit, or the actual limit here, this limit is definitely not going to exist. It doesn't exist because, well, number one, the left-hand limit and the right-hand limit are not the same, and they're also infinity. So this has no chance of existing. So this limit just does not exist. There's another topic in this section that will come up that you're probably familiar with from an algebra class, and that is vertical asymptotes. So if you remember the good old fun days in algebra class, when you're trying to find a vertical asymptote of maybe a rational expression, and if you remember what you would do, you would probably, as a recall here, set the denominator equal to 0. And solve for x. Typically it'd be x, whatever the independent variable is. You solve for x, and you would do that to find the vertical asymptote. And the answer would be x equals some number, and that would be the vertical asymptote. And there's, some things you had to be careful about. You had to make sure that the numerator also didn't have that same root, so to say, because then it would mean there's a hole in the graph. But typically, this is the process you would go through. Set the denominator equal to 0 and solve for x. And then this line x equals a, and the key here is it is an actual line, right? And the way we write it is x equals a. Remember, vertical asymptotes look like x equals a. What about horizontal asymptotes? Do you remember what they look like? They'd be like y equals some number, right? Y equals 3 or whatever would be horizontal. But vertical, they always look like x equals a. And you get a vertical asymptote of the curve y equals f of x if at least one of the following things here is true. So maybe you have a function that does something like this. So it's approaching a from the left and it just goes up to infinity. Or maybe it's approaching a from the left and it goes all of a sudden to negative infinity, to never to return. Or maybe you're approaching over here approaching a from the right, and as you approach a from the right, maybe the function does something like this. It just never crosses the vertical asymptote. And also you could be approaching a from the right, and maybe it does something like this. So in each of these cases, what I'm trying to show is that this graph never crosses the vertical asymptote. So you have graphs that look something like this in each of these four cases. And in each of these cases, the line x equals a, this line x equals a is the vertical asymptote. So now let's look at some examples where we run into things like this with these vertical asymptotes. So our first example, get the limit as x approaches 5 from the left of this expression. And we can think of this graphically, but what I really want us to concentrate is thinking of it analytically. And it's a little tricky to do that, but it's something we have to be able to do as a calculus student. So first we'll concentrate on the graph. So just think of like if you have the graph of y equals 1 over x, which we've seen before. Well, if I change this 1 to a 6, I have y equals 6 over x. It's still pretty much the same shape, right? It's not going to do much. And then this x minus 5 is just going to shift this graph to the right 5 units. So we know basically the graph of 1 over x does something like this. So the graph of 6 over x is going to be similar, right? It'll just be, everything will be multiplied by 6, but it's going to basically have the same shape. And then this is going to move this thing over 5 units to the right. And, you might be a little rusty on those things, but I'm sure you covered them at some point in algebra class. So I move over 1, 2, 3, 4, 5. And then from here, I would basically have this vertical asymptote would be shifted over to 5, to x equals 5. So you'd have like this asymptote here. And then we have basically the same graph. So as x approaches 5 from the left, you can see from the graph, this is the line x equals 5. When I approach 5 from the left, this is going towards negative infinity. So I can see the answer is negative infinity. But we want to not rely on a graph. So we want to think of it analytically instead. So let me show you how we do this in a calculus class. When you think of these things analytically, we can think of if we have this number line here, and we're approaching 5. So let's say there's a 0 here. 1, 2, 3, 4, 5, 6. So if I'm approaching 5 from the left, I'm coming in 5 from here. So I'm coming in from numbers like 4.9, 4.99, 4.999. And I plug these numbers in for x, right? So I'm going to get a number really close to 5 but smaller than 5. So really what I'm going to get a 6 on the top. The numerator will be 6, right? This doesn't affect the numerator, still 6. Now the denominator, as I get closer and closer and closer to 5 from the left, so numbers smaller than 5, I'm going to get numbers really close to 5 but smaller than 5. So when I do the subtraction, I'm going to get a really tiny but negative number. And the way we show that is this. We put negative 0. Now we know negative 0 doesn't really have a meaning, right? I mean, 0 is 0, but what we're trying to show here is that I've got this denominator approaching 0 through negative numbers, right? Because I can get really close to 5, but I'm coming in from the left, so they're going to be numbers less than 5. I subtract them from 5, I'm going to get a really tiny but negative number. So then just think, what would be a constant 6, a positive constant, divided by a really tiny negative number, like smaller and smaller and smaller, but always negative? This thing is going to be a huge negative number. The limiting value will be negative infinity. So we can just say that the limit of this is negative infinity. Maybe I probably should have moved this over here a little bit. But basically, I'm just showing that the numerator is 6. The denominator, this denominator, as x approaches 5 from the left, is going to get really, really tiny, but always negative. So 6 divided by a super tiny negative number, you could think of that, is negative infinity. This next one, B, I want you guys to try out a second, but I want to give you a hint on this. You can see the numerator. There's not really an issue up here. If I plug in a -3 here, although I never really get to -3, but if I think of a number really close to -3, it's basically just going to be kind of like a -1 up here, right? -3 plus 2, this is going to be a number really close to -1, not a problem. The problem is down here, I'm going to get something that is going to be like division by 0. If I were to just plug in -3, I would get division by 0. So we have to be concerned with the denominator. The numerator, you can treat it like a -1, and you want to think about what's happening to the denominator as x gets really close to -3 from the left. So take a few minutes, press pause, and see if you can figure this one out, and come on back, and we'll see how you did. Okay, so for this one, again, I hope you guys are taking some time to try to figure these out. So I'm going to think of a number line again. So I'm approaching -3. So I'm going to go -4, -3, -2, -1, and 0. All right, so I am approaching -3 from the left. So I'm coming in from here. So I'm coming in with numbers like -3.01, -3.001, -3.0001, and things like that, right? These numbers that are less than -3, they have a larger magnitude, but it's a bigger negative number, so it's less than, right? So what we really got happening, the numerator is essentially -1, because I've got a number really close to -3 I plug in here. So I added 2, it's -1, something really close to -1. So it's not really important. What's important is down here. So I'm plugging in numbers like this. So if I take -3.0001 plus 3, I'm going to get a negative number. It's going to be a really tiny number. So essentially, I'm going to get a -0. So long term, what we've got is a constant divided by a number that's really close to 0. And since it's so tiny, it's going to make this whole thing large. Then we've got negative divided by negative, which is positive, so that this thing actually reaches infinity. So it approaches infinity. And you could graph that if you wanted to look, but we want to be able to not depend on a graph. We want to be able to think of it analytically like this and see that it's going to be infinity. Now this next one that we look at, if you actually plug it into your graph, it confuses graphing calculators. So it's actually not easy to even look at this one on the graph and figure out what's happening. So this one will be easier just to, again, try to think of it analytically. But first, let's think about what the natural log function looks like when you graph it. And logarithms all look something like this, where they go through at 1. So the natural log, if this is y equals natural log of x, well, if you plug in a 1, natural log of 1 is 0. And that's true of any base. All logarithms look something like this. They go off at steeper angles. So they might be a little flatter here or a little wider, but they all go through here at 1. So if I change this to the log of x, it'll still go through here at 1. Or log base 7, log base 12, whatever base you want, it's going to go through here at 1. So they all have this kind of look to them, any logarithm function. So what we've got is a natural log of x squared minus 16, and x is approaching 4 from the right. So I'm just going to do this number line idea again. So here's 0, here's 4, and here's 5. I'm approaching 4 from the right, so I'm coming in from values bigger than 4. Right, so these are values like 4.01, 4.001, and so forth, bigger than 4. And then I'm squaring them. So I'm squaring numbers bigger than 4. So they're going to be numbers bigger than 16. Then I subtract 16 so that basically this argument to the natural log, the input to the natural log, is going to be tiny but positive. Right, because this x that I'm plugging in here is going to be a number a little bit bigger than 4, but not much bigger. Really close to 4, but a little bit bigger. So when I square it, it will be a little bit bigger than 16. Then I subtract 16, so I'm going to get a tiny but positive number. So the question is very similar to what's the natural log of a really tiny but positive number. Well, here's a natural log function. So if my input is a really tiny but positive number, the natural log at that point is heading towards negative infinity. So the answer to this question is going to be negative infinity. All right, this brings us to the last question, which is the limit as x approaches pi from the left of cotangent of x. Well, some of you, I'm sure, have looked at the graph of a cotangent function, maybe in a trig class. But I can tell you that most calc students don't really remember this graph if they've seen it in the past. So what we can do, though, I mean, if you remember the cotangent graph, you can just think of the cotangent graph and you can answer this question that way. But what we could also do is just think, whenever you're not sure about a trig function, you can always write it in terms of sines and cosines. So maybe we'll do this a couple of ways. Okay, so let's say you remember the cotangent graph. And the tangent graph is always increasing. The cotangent graph is always decreasing. And if you remember that cotangent is cosine over sine, you'll know that wherever sine is 0, the cotangent graph is going to have a vertical asymptote. So all these integer multiples of pi. So the cotangent graph is going to be doing something like this. It's going to be 0 wherever cosine is 0, which is at multiples of like pi over 2, right? So if this is the origin right here, we've got like pi here, 2 pi, this is negative pi. The cotangent graph is always decreasing. So as x approaches pi from the left, so we're coming from the left, you can see the cotangent graph is going towards negative infinity. All right, so the answer is negative infinity. But I think many of you will not really be familiar with the cotangent graph. So I'm going to also do this using sines and cosines, which I think will be more familiar for most of us. So let's do this. I told you before that it's important to know the sine and the cosine graph. We really have to know these. Because what we can do here is we can say, well, this is the same as the limit as x approaches pi from the left of cosine of x over sine of x. And then these two graphs, y equals sine of x, y equals cosine of x. These are two we just absolutely have to know. If we want to be successful in calculus, we have to know these two graphs. So the sine goes through like this, cosine goes like this, and this is pi to pi, and of course they go on forever, right? I'm just putting one period here, but one like complete revolution of these, but they go forever, right? In both directions, they keep going on. But for us to answer the question, we just need this. We need to concentrate on right here. So here's the sine. So think about the limit as x approaches pi from the left of sine. So I'm coming in here. The sine curve is going to 0, but through positive values, right? Every y value here is positive. So as x approaches pi from the left, so x is coming in here, the sine curve is approaching 0 through positive values. So I'm going to think of this as positive 0, right? It's the sine graph. The sine graph is going to 0 through positive values. Now the cosine graph, on the other hand, this is just getting really close to negative 1. As I approach pi from the left, this is getting really close to negative 1. So I basically just have a negative 1 here. So you can interpret this Remember, plus 0 doesn't really have a meaning, but we use it when analyzing limits, usually in a calculus course, just to think of what I mean here by this notation is I've got really tiny but positive numbers. So if I've got a -1 divided by a really tiny but positive number, I can make this as large negative as I want, right? Like take in your calculator, put -1 divided by 0.00000001, and you're going to get a large negative number. And we're looking at a limiting value. So the smallest, as this gets really, really, really small, this overall is going to be approaching negative infinity. So the answer is negative infinity. All right, so that should give you everything you need for section 2.2. Just remember the only way you will get good at calculus is to do calculus. So make sure you do your homework and make sure you bring any questions you have to me and we will take a look. So with that, go ahead and get started on your homework and I will talk to you soon.